Hi everyone, we're going to pick up with section 10.2 now, which is how do you do all the stuff that you probably learned back in Calculus 1 about derivatives and slope, and how do you do the stuff from Calculus 2 with integration, finding the area inside of a curve and things like that. We're going to do that with parametric curves now. So that's what this section is about. So when we want to find derivatives, our derivatives of a parametric equation, you still are after the same dy dx that we wanted back in Cal 1. It's just now our y is a function of t and our x is a function of t. And so to find the dy dx, you have to do a little bit of manipulation. So looking at this formula right here, dy dx equals dy dt over dx dt. And we don't want the derivative of x with respect to t to be 0, because you don't want to divide by 0. And then if you wanted to do the second derivative, this is the second derivative of the y with respect to x both times. That would be the derivative with respect to t of the first derivative divided by the dx dt again. You'll learn why that you have to divide by this little extra dx dt. Usually pick up the y in that. If you take my class for differential equations, I go through that. But you'll definitely see it in Cal 4 if you're going to Cal 4 as well. If you're not taking either one of those, then just take my word for it. You have to divide by dx dt. So this says find dy dx if you know x equals t over 1 plus t and y equals the square root of 1 plus t. And so remember, your dy dx will be dy dt divided by dx dt. So what I want to do is kind of go off to the side and find these two derivatives, this dy dt and this dx dt. I'm going to start with the x. So your dx dt is, since x is t over 1 plus t, that's a quotient rule. You would do the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. You might remember from Cal 1 that if your power for your variable on the top and the bottom are the same, that variable usually cancels off. That's still true. If you didn't know that, now you do. You'll end up with 1 plus t minus t on top over 1 plus t squared. And so, like I said, the t's actually cancel each other off. And so we're left with, oops, pick the same color here. We're left with 1 over 1 plus t squared. For the derivative of, for y, I have a square root. And so you have to kind of keep in mind that the square root is the same thing as a 1/2 power. So we're going to do the chain rule on this to find dy dt. So dy dt would be pull the power down, leave the inside exactly the way it is, to the 1 less power, times the derivative of the inside. The derivative of the inside, the derivative of the t is just 1. So we're left with just 1 over 2 times 1 plus t to the 1/2. Or if you want to switch it to 1 over 2 times 1 plus, oops, sorry. I was going to switch it to a square root. So if I switch it to a square root, it would go back to the square root of 1 plus t. So either one would actually be okay. So my derivative over here, dy dx, would be the dy dt. I like the 1/2 power notation just because you'll notice there's a 1 plus t on the bottom of the x and the y after its derivative. So hopefully I can combine them together. So I'm going to use the 1 over 2 times 1 plus t to the 1/2 divided by the dx dt which is just 1 over 1 plus t squared. And then we can do a little bit of simplifying. So we can simplify it because I can take the bottom fraction, flip it over, and multiply it. So your dx dt is 1, or dy dx, sorry, is 1 over 2 times 1 plus t to the 1/2 power times 1 plus t squared over 1. So the squared on top and the 1/2 power on the bottom can combine together. You just subtract those powers, 2 minus 1/2, to get 1 plus t to the 3/2 power. And that would be your derivative for dy dx. So hopefully that is not too bad. I don't think it is. But like I said, it's going to get a little bit worse than that as we go along. So that's kind of a simple one to start with. Let's do another one. Dy dx, find dy dx. If you know that y equals t plus sine t and x equals t e to the t. So we'll have dy dt sitting on top, dx dt sitting on the bottom. And again, I have to find these things. So your dx dt, since this is t e to the t, that's a product rule. So I have to do the first times the derivative of the second plus the second times the derivative of the first. So I'll end up with just t e to the t plus e to the t. And that's my dx dt. dy dt is actually pretty simple. No product rule or anything. The derivative of t would just be 1. Derivative of sine is cosine. Hopefully you remember all your derivatives along the way. So I just divide these two things and I'll end up with my dy dx. So I'll get 1 plus cosine t on top. On the bottom, I'll end up with t e to the t plus e to the t. And sometimes they don't simplify very much, and in this case, nothing's really going to cancel like it did on the last one. So I'll just stop right there. That would be my derivative, dy dx. So that one was pretty easy. This one says, find the equation of the tangent line to the curve at a point corresponding to a parameter t negative 1 in this case. So very much like what we would have done back in Cal 1. Your equation of a tangent line, you have to find the derivative to find the slope. And you need a slope and a point to come up with the equation of the line. So we're going to start with the derivative first. So first thing I got to do is find dy dx. And just like on all the other ones we've done so far, it is dy dt divided by dx dt. And so I got to find these derivatives. These are both just power rules. This is actually fairly easy to do. Dx dt, the derivative of the x, would be a 3t squared. And that's it. The plus 1 goes away. And dy dt, the t to the fourth would become 4t cubed. And the plus t would go to a plus 1. So that's kind of our side work up here at the top. And so our derivative is the dy dt, which is the 4t cubed plus 1, divided by the dx dt, which is 3t squared. And that's my derivative. Now, you can simplify this a little bit if you want to. Since it is just a single term on the bottom, you could divide it into each one. Or you could leave it the way it is. I'm going to leave it the way it is, actually. And that way I know that my slope is my derivative, dy dx, evaluated at negative 1. So this negative 1 right here gets plugged in to my derivative. And so I'll end up with 4 times negative 1 cubed plus 1 over 3 times negative 1 squared. Negative 1 cubed is negative 1 times 4 is negative 4. On the bottom, negative 1 squared is just 1 times 3 is 3. So I'll get negative 3 over 3, which is negative 1. Now, it is purely coincidental that the slope of negative 1 is the same as the t-value. That's not hardly ever the same thing. But now we have a slope. We also need a point. We got to have a number for the x and the y. And we get that number by taking this t-value and plugging it back in to both the x and the y. So when t equals negative 1, then the x point is negative 1 cubed plus 1. Negative 1 cubed is negative 1 plus 1 would be 0. And your y would be negative 1 to the 4th plus negative 1. Negative 1 to the 4th would make a positive 1, plus the negative 1 would also make 0. So my point that I have to use is the point 0, 0. Again, a little bit more side work. And then you just do the equation of a line like you would have done back in Cal 1. I'm going to use y minus the y value is the slope times x minus the x value. So what we have here is y minus 0 equals negative 1 times x minus 0, or y equals negative x. That's the equation of my tangent line to the point 0, 0 in x and y, corresponding to the parameter when t is negative 1. Let's try another one of that same type. Here, this one's going to be a little bit more complicated since we have t cosine t and t sine t, and we're plugging in pi, but I want to try doing the same sort of thing. So I'm going to find dy dx, again, because I have to find the derivative to come up with my slope. And just like before, this is dy dt divided by dx dt. Now your two derivatives here, though, for the dy dt and the dx dt, these are going to be product rules. You have a t that's multiplied by cosine and a t that's multiplied by sine. So the derivatives are a little bit more complicated, but not too bad. So your dx dt will be the first one times the derivative of the second. The derivative of cosine is negative sine plus the second times the derivative of the first. So I'm left with negative t sine t plus cosine t. And then my derivative for y will look actually very similar. I'll have the first times the derivative of the second one, which would be cosine t, plus the second one times the derivative of the first, which would just be 1. So I'm left with t cosine t plus sine t. This would be my side work for my derivatives. And so my derivative itself, dy dx, would be t cosine t plus sine t, all divided by negative t sine t plus cosine t. Again, this does not simplify very well, so we're going to leave it just like that for the derivative. And so I'm going to plug in a point anyway. So my slope would be the derivative evaluated at pi. This t value right here gets plugged in to my derivative. And so I'll get pi cosine pi plus sine pi, that's sine right there, divided by negative pi sine pi plus cosine pi. Then you have to pull off your different values for sine and cosine at pi. Cosine at pi is negative 1, so I get pi times negative 1. Sine of pi is 0. Then on the bottom, I'll get negative pi times 0. And then cosine of pi, again, is negative 1. So all I'm left with is a negative pi divided by negative 1. which is pi. So I get a slope of pi. Now, I just stated on the last problem that you don't always get the t value to be the slope, and then I just showed you another one where you did. Again, that does not always happen. Just take my word for it. And so now that we have a slope, I also got to figure out what the x and y are. So I need to take this pi and plug it back in. So when t equals pi, let's make that a little bit darker. That's kind of hard to see. When t equals pi, my x would be pi cosine pi. Well, cosine pi is -1, and -1 times pi would be negative pi. If I plugged in pi for the y, I'll get pi sine pi. But sine of pi is 0, so I just get 0. So I get the point negative pi 0, which is kind of a strange looking point. Then I go back to my y minus y1 equals the slope times x minus x1, the point slope formula. And I'll say that y minus the y value, which was 0, equals the slope, which was pi, times x minus the x value, which was negative pi. So I'm left with y equals, and I'm going to multiply the pi across and get pi x. And the negative and the negative make positive. Pi times pi gives me a double helping of pi, which is pi squared. And that is my equation of my tangent line, which isn't too bad. Okay, now we're going to try to do it two different ways. We're going to find the equation of the tangent line first, the way that we were doing it just on the last few problems. Don't eliminate the parameter and find the dx dt, the dy dt, and that sort of thing. Secondly, we'll do the exact same problem again, but we will eliminate the parameter along the way. So first thing I'm going to do is the same thing we were just doing in the last problems. So I want to find dy dx by doing dy dt over dx dt. And these aren't terribly hard to do. My dx dt, the derivative of the 1 would be 0. The derivative of the natural log of t would just be 1 over t. You might remember that from Cal 2 when you talked about logarithms. For the derivative of y with respect to t, I would end up with a power rule. T squared becomes 2t. And the plus 2 just goes away. So my derivative down here, again, this is just my side work. My derivative would be natural log, would be 2t divided by the 1 over t. So if I flip that over, I would get 2t times t over 1. Or I just get 2t squared. Now notice, they do not give me a t value here, but they give me a point, the 0.13. So here we're going to go backwards. Instead of having a t value and then we finding a point, we'll have a point that we have to correspond to a t value. So you have to figure out what t value will give you these two numbers from these two equations. And so just pick, for instance, the first one. If x equals 1 plus natural log t, and my x value is 1, just do 1 equals 1 plus natural log t, and solve it for t. That would give me 0 equals natural log t, and you might remember from Cal 2 that, that doesn't look too good. Natural log t? Well, it's okay. You might remember that natural log of 1 gives you 0, or you can exponentiate both sides. But either way, t would be 1. I do suggest that whatever you get for one of them, plug it in the other one to make sure. So if I have that t is 1, if I did y equals 1 squared plus 2, I would get that y equals 3. That checks out because my 3 is what I got for the other point. So my t value that I'm going to use is 1. Then if I want to do my slope, I will do dy dx at 1. That'll be my slope. And so here I just do 2 times 1 squared, which is 2. I have the point already of 1, 3, so I would do y minus the y value is the slope times x minus the x value. Notice the slope did not come out to be the same thing as the t value in this case. So I get y minus 3 equals 2x minus 2. Add the 3 to both sides, so I'll get 2x plus 1 for the equation of my tangent line. That's the first way you could do it. The other way is you could eliminate the parameter. If you want to eliminate the parameter, you got to get rid of the t. So what I'm going to do is I'm going to take that first equation, the x equals 1 plus the natural log t, and I'm going to see if I can't solve that for t. So I'm going to have x minus 1 equals natural log t, and then I'm going to exponentiate both sides. So if I exponentiate both sides, the natural log and the exponential will cancel to give me that t equals e to the x minus 1. Then I can plug that value into y, and then I'll have eliminated my parameter like we did in the last section. And so y would be the t squared plus 2, but I'm going to replace the t with e to the x minus 1. And so y would be a power raised to a power means you just can multiply the powers together. So this is e to the 2x minus 2 plus 2. And now I have eliminated my parameter. Then if you want to find the equation of a tangent line, you do this just the same way you would do in Cal 1 and Cal 2. Take its derivative. So y prime would be the derivative of the power would be just 2. The exponential doesn't change, and the plus 2 goes away. I would plug in the 1. That's from over here. I would plug in the 1 for my x value to figure out my slope. So my slope would be y prime at 1, which would be 2e to the 2 times 1 minus 2. Or my slope would be 2e to the 2 minus 2, which is e to the 0. E to the 0 is 1. So my slope is 2. Now, from that point right there, it's the same as it is over here. I have a slope of 2, so then I would use this equation, plug the 1 and the 3 in, and you get the same points. You would get that y equals 2x plus 1 the same way. But it doesn't really matter. You can eliminate the parameter, or you could not eliminate the parameter. A lot of the times, it's easier to not eliminate the parameter if your problems get extremely complicated. But it could be done both ways. Okay, this one says find the equation of the tangent line and sketch the graph as well. So hopefully that's not too bad. Remember, we did curve sketching and things in the last section. So I started the same way. I'm going to do it by finding the dx dt and the dy dt, just because I think that is more important as we go along through the semester. So your dy dx would be dy dt divided by dx dt. So your dx dt, again, simple power rule. The t squared minus t becomes 2t minus 1 by the power rule. The dy dt will become 2t plus 1. The plus 1 on the end on the y doesn't matter. And so my derivative here would just end up being 2t plus 1 divided by 2t minus 1. Please do not cancel the 2t's off and say the answer is negative 1. Don't do that. I know none of you are thinking that, but I'm going to tell it to you anyway. And so then my slope, actually let's do that in black. My slope would be the derivative evaluated at something. And so it doesn't tell me the t value, so much like the last one, we'll have to figure out what that t value is. So let's take it from the x like we did last time. The x is 0. X is 0. So if I set 0 equal to t squared minus t, you bust out your best algebra skills and you notice that that can factor. This is t times t minus 1. So t is either 0 or t is 1. You cannot use both. One of them is correct and one of them is not. So what you have to do is take both of those, plug it into y, and see which one gives you the 3 from the point. And it's going to be the t equal to 1. So if you do the 0, you'll get 0 squared plus 0 plus 1, which is 1. But if you did the 1 plugged in, 1 squared plus 1 plus 1, that one's 3. That's the one that checks out with the point from over here. And so t equals 1 is the one that we're going to use. So that 1 goes in right here. And so I'll have 2 times 1 plus 1 over 2 times 1 minus 1. That's 2 plus 1 over 2 minus 1, which is 3 over 1, which is 3. I have a slope. In this case, I actually have the slope and the y-intercept. 0, 3 is the y-intercept. So you could do just y equals mx plus b if you wanted to. If I do that, I'd get 3x plus 3. That's the equation of my tangent line. As far as the graph is concerned, depends on how well you can draw this out. I want to draw the actual the graph of the x and y first, and then put the equation of the tangent line on top of that. And so we'll do that first. I know when t is 1, I get the point 0, 3. So numbers are going to probably be kind of small, so I won't make it too big. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hopefully that'll fit it all on there. If not, we can adjust. I'm going to make a little table down here where I have different t values, x values, and y values. And let's just start with 0. We'll do 0, 1, 2, kind of see what it looks like. If t were 0 and I plugged it in for x, I would get 0, and if I plugged it in for y, I would get 1. I already know that from this top right hand side up here, that when t is 0, I get 0 for x and I get y as 1. If t is 1, I get the point 0, 3. I already know that from the point that was given to me. If I plug in 2, 2 squared is 4 minus 2 would give me 2. If I plugged in 2 into the y, 2 squared is 4 plus 2 is 6 plus 1 is 7. So at 2, I am at 7. So I have the point 0, 1, 0, 3, 2, 7. Oops, right there. And so I'm going in a direction kind of around it. You might want to plug in what happens at, say, 1/2 to see whether or not you're on the left or the right-hand side of the axis. But I'll tell you, if you plug in 1/2, you'll get a graph that's going around this way. And then it'll go up this way. And our arrows would go in that direction. My tangent line is 3x plus 3. So I have to go up to 3. So there's that point right there. That point right there. And then I go up 3. 1, 2, 3, and over 1. And depending on how good of a drawer you are, oh, change the pen width there a little bit. This is supposed to be a straight line, tangent line, up against the side of that graph. That's also another reason that you know that it's kind of going to the left first before it turns up to the right. If you did it the other way around, your graph wouldn't hit the tangent line in the right way. Okay, let's talk about concavity and your second derivative. You might remember that from Cal 1. The second derivative tells you whether or not you're concave up or concave down. So this question says, can you find the derivative and the second derivative, and then find the values of t to locate where the curve is concave up. So we're going to start by finding derivatives first. So dy dx is dy dt divided by dx dt. And so for my derivatives, these are actually really easy, especially the first one. Dx dt, the derivative of e to the t is e to the t. It does not change. The derivative on the second one, though, a little bit harder. It's a product rule. It's a t e to the negative t, so I have to do first times the derivative of the second plus the second one times the derivative of the first. So this gives me negative t e to the negative t plus e to the negative t. So a little bit of side work here. But my derivative becomes the dy dt, which is the negative t e to the negative t plus e to the negative t divided by e to the t. Now you can simplify this one because the exponential on the bottom could divide into the top if you wanted to. I'm going to go ahead and do that. So you could divide it into each one, moving that t up, and you'll end up with a negative t e to the negative 2t plus plus e to the negative 2t. And so that's my first derivative. It asks you to find the second derivative as well. Now, one reason I wanted to combine those together was because your second derivative, you have to take the derivative of the first derivative, and so that's why I went ahead and did that. So your d squared y over d x squared, your second derivative, is the derivative of the first derivative, dy dx, with respect to t, divided by dx dt again. So I have to take the derivative of this thing that I just found with respect to t. So that first part, the negative t e to the negative 2t, that is a product rule. So I would do the first one times the derivative of the second, which is negative 2 e to the negative 2t, plus the second, it's a plus e to the negative 2t, times the derivative of the first, which is just negative 1, and then the e to the negative 2t would become a minus 2e to the negative 2t. So that would be the derivative of dy dx with respect to t. Then I have to divide the entire thing by the same e to the t that was the derivative of the x, the dx dt. And then we simplify this a little bit. This is positive 2t e to the negative 2t minus e to the negative 2t minus 2e to the negative 2t divided by e to the t. So the last two terms could actually combine together to give you 2t e to the negative 2t and then a minus 3e to the negative 2t, all divided by e to the t. Or we could divide the exponential into each one, much like we did on the first derivative, and come up with 2t e to the negative 3t minus 3e to the negative 3t. And that could be your second derivative. Now, if you remember, to do concavity, you had to find what are called inflection points. You might remember that sort of thing. So you really want to figure out what makes the second derivative positive or negative. We're looking for, on our problem, where is this thing concave up? So we want this equation down here at the bottom, this second derivative, to be greater than greater than 0. Equal to would be the inflection point. So we want it greater than 0. So I'm going to do that on this lower left-hand portion of the screen here. I want 2t e to the negative 3t minus 3e to the negative 3t to be greater than 0. Now, in this case, what it might be easier to understand is maybe I should drop that exponential back to the bottom and rewrite it as 2t minus 3 divided by e to the 3t. For this fraction to be greater than 0, e to the 3t is always going to be greater than 0. It's an exponential function that's always positive, no matter what value t you plug into it. So the bottom doesn't even matter. It's really, where does 2t minus 3, where is that greater than 0? And so that would be where 2t is greater than 3, or where t is greater than 3 halves. So as long as you pick any value of t bigger than 3 halves, or you could write it in interval notation, 3 halves to infinity. As long as you pick any value of t greater than 3 halves, your function should be concave up. And if you go the other way, probably concave down, anything less than 3 halves. Let's do it again. T minus natural log t and t plus natural log t. I'll do the exact same process again. Finding dy dx to begin with. That is your dy dt divided by dx dt. And so my derivative for x, my dx dt, would be 1 minus 1 over t. So the natural log of t goes to 1 over t. The dy dt would go to 1 plus 1 over t. And so if I divide those two things, I'll get 1 plus 1 over t divided by 1 minus 1 over t. Again, this is just the side work. Now, what I would do in this case is multiply everything in this problem by t. And so I would have a t plus 1 over a t minus 1. That would be my first derivative. As far as my second derivative goes, t squared y over dx squared. That would be the first derivative, dy dx. And you take the derivative of that with respect to t, and do not forget to divide by dx dt. That's one of the number one mistakes people make on the test and such, is they forget to divide by that extra dx dt. So this says take the derivative of the function I just got. Well, that's a product, not a product rule. You could make it a product rule, but it is a quotient rule the way it's written. So I'm going to do it as a quotient rule. It would be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. But don't forget to divide by the extra 1 minus 1 over t. And then we just need to simplify this thing. The top part is just t minus 1 minus t minus 1 all over t minus 1 squared, all divided by that same 1 minus 1 over t. I mentioned before, if you ever have a power that's the same on the top and the bottom and you do the quotient rule, there's a good chance that that power will cancel, and that does happen here. So at that point, I'm left with just a negative 2 over t minus 1 squared. And on the bottom down here, I'm going to put it as a common denominator so that we can flip it and multiply it. So if I were to get a common denominator, this 1 would be t over t. So I'd have this be t minus 1 over t. That way on the bottom I get negative 2 over t minus 1 squared. And then I can multiply it times t over t minus 1. And the t minus 1s can combine together to give me negative 2t over t minus 1 cubed. And that would be my second derivative. From there, I want to know where does it end up being positive again. So the up, concave up, is greater than 0. Remember that. The concave down is less than 0. So I want to know where is this second derivative. Where does negative 2t over t minus 1 cubed, where is that greater than 0? Well, in this case, I can't get away with the little trick that I did last time, where the bottom was always 0, or always bigger than 0. Here, I actually have to figure out what makes the top part equal 0, what makes the bottom part equal 0, and do much like what we would have done in Cal 1. The top gives you 0, negative 2t equals 0, where t is 0. And the bottom, t minus 1 cubed, equals 0 when t equals 1. So then what I would do is I would draw a number line, putting the numbers 0 and 1 on this number line. And I would pick different values in between to plug back in. Like maybe I'll plug in 2 or 1/2 or negative 1. And those have to go back into my second derivative. So let's say I plug in negative 1. I would get negative 2 times negative 1 over negative 1 minus 1 cubed. That gets me 2 over negative 1 minus 1 would be negative 2 cubed, which is negative 8. That's negative 1/4. The number doesn't matter, but it comes out negative. So that is not where it's concave up. That would actually be where it's concave down. If I plug in the 1/2, I'll end up with negative 2 times 1/2 over 1/2 minus 1 cubed. So on top I get negative 1. On the bottom I get negative 1/2 cubed. Now I don't know, you could work it out. It's positive 8, I believe. But you don't have to work it all the way out. Negative 1/2 cubed would be negative 1/8, and negative 1 divided by negative 1/8 would be positive 8. But the only thing you really have to know is whether or not it comes out to be positive or negative. Since I have a negative on top and a negative on bottom, two negatives divided make a positive. And if you check the 2 times 2, negative 2 times 2, over 2 minus 1 cubed, that would give me negative 4 over 1, which is negative 4. So the only spot I care about is this little spot right here, between 0 and 1. So my answer for where would it be concave up, it is concave up for any value of t between 0 and 1. Or if you want to write an interval notation, 0 to 1. Either one. Okay, let's find the points on the curve where the tangent line is horizontal or vertical. Horizontal or vertical. So a tangent line is horizontal when you have a slope of 0. It'll be vertical when you have an undefined slope. So that's what we're going to start with. We got to find the slope. So your dy dx is your derivative, dy dt, divided by dx dt. And so let's find these derivatives. Dx dt would be a power rule, 3t squared minus 3. Dy dt is also a power rule. That becomes 2t. The minus 3 goes away. And so I just get 2t divided by 3t squared minus 3. And that would be my derivative. And then I have to pull off, what do all these other things mean? Well, you get horizontal on a parametric equation where your dy dt, your top part of your derivative, that's where dy dt is equal to 0. And so we want to figure out what makes 2t equal 0. Well, that means t is 0. If you're looking for the actual point, like we're looking for here, we're looking for the points on the curve, then you have to plug the t back in for the x and the y. So the x would be 0 cubed minus 3 times 0, which is 0. And the y would be 0 squared minus 3, which is negative 3. So my point, where it's horizontal, would be 0 and negative 3. To do vertical, that's where my dx dt is equal to 0. So I'd have 3t squared minus 3 equals 0. That would give me 3t squared. Oops, that's supposed to be a squared. Equals to 3. Or t squared equals 1 if you divide by 3 on both sides. So t would be plus or minus 1 if you took the square root. So here we have two vertical locations and one horizontal. Both the 0, like up at the horizontal when I plugged it into the x and the y, the 1 and the negative 1 also have to be plugged in as well. So x, when it's at negative 1, I'll have negative 1 cubed minus 3 times negative 1. This would be negative 1 plus 3, which is 2. And then I also have to plug in positive 1. And if I plug in positive 1, I'll get 1 cubed minus 3 times 1. That'll actually give me negative 2. 1 minus 3 is negative 2. And then I plug in the negative 1 and positive 1 into the y. So y for the negative 1 gives me negative 1 squared minus 3. That's 1 minus 3, or negative 2. I plug in positive 1, I get 1 squared minus 3, which is, well, negative 2. So I'll get the points 2, negative 2, and the point negative 2, negative 2. So these 2 points are vertical, and then I have one horizontal point. So hopefully that's not too bad. This one says, show that the curve x equals cosine t and y equals sine t cosine t has two tangents at 0, 0, and find their equations. And then we'll sketch the curve a little bit. So there should be two tangent lines at 0, 0. And we'll see what those are. Remember, your tangent line comes from your first derivative, so dy dx equals dy dt divided by dx dt. So my derivative for y, sine, cosine, that's actually a product rule. If you want to do the product rule, your derivative would be the first times the derivative of the second. Cosine would go to negative sine plus the second times the derivative of the first. Sine goes to cosine. Bottom one's a little bit easier than that. No product rule or anything. Derivative of cosine is, in fact, negative sine. And so the top part is actually cosine squared minus sine squared over negative sine t, if you want to leave it like that. Or you could flip them and say that this is sine squared minus cosine squared divided by positive sine t. It actually does not matter. But if we have two tangent lines, then I need to find the values that would give me that point. I need the t values for the 0, 0 is what I'm looking for. So what t values give you 0, 0? Well, let's try using the x first. So if I take this 0 and let that be the x value, I would have 0 equals cosine t. So where does 0 equal cosine t at? Well, cosine 0 in two locations, pi over 2 and 3 pi over 2. Now, I mentioned earlier, whatever t value you get for one equation has to make the other one true as well. So if we have two tangent lines, both of the pi over 2 and the 3 pi over 2 have to make the y be 0 as well. So if I plug those in for the y, then I'll get that y equals sine pi over 2 cosine pi over 2. Well, since it has a cosine pi over 2 on it, that would be 0. And if I plugged in 3 pi over 2, I would end up with sine 3 pi over 2 cosine 3 pi over 2. But again, since it has a cosine 3 pi over 2 on it, it's still 0. So both t values make this work. So I should have two tangent lines at this spot. To find out what they are, we plug both of those values in to figure out the slope. So my slope for one of them is plugging we'll start with the pi over 2 into the derivative. I'll get sine squared at pi over 2 minus cosine squared at pi over 2 divided by sine pi over 2. Now sine of pi over 2 is 1, so I'll get 1 squared. Cosine pi over 2 is 0, so I'll get 0 squared over 1. This is 1. This has a slope of 1. A slope of 1 with a point 0, 0 tells me I have an equation of a tangent line of just y equals x. 0, 0 is the x and y intercept here. And if you plug in the other one, dy dx, for 3 pi over 2, I'll get sine squared of 3 pi over 2 minus cosine squared at 3 pi over 2, all divided by sine 3 pi over 2. Sine at 3 pi over 2 is actually negative 1, so I'll end up with negative 1 squared. Again, cosine 3 pi over 2 is 0, so I'll get 0 squared divided by negative 1. This is actually negative 1. This will give me an equation y equals negative x. And that would be my two tangent lines. The curve of this thing looks kind of like an infinity sign. And we'll talk more about how to do curve sketching as we get further along throughout the semester. But you end up with a thing that kind of looks like, if it comes over to 1 and over to -1, you could plot some points if you want to. I'll let you all do that part if you want to do all the plotting the points and everything. But we end up with a graph that kind of comes up and then back down and then back down like this. And our two tangent lines, one of them, y equals x, goes this direction. And our other tangent line, y equals -x, would go this direction. And that's why we end up with 2, because it's looping back through the origin. This one says, at what points on the curve, the 3t squared plus 1 and the t cubed minus 1, does the tangent line have a slope of 1/2? So to do this, what we have to do is we find the derivative, because the derivative represents the slope, and set it equal to 1/2 and solve it. So our dy dx would be the derivative of the y, which in this case would be 3t squared, the minus 1 goes away, divided by the derivative of the x, which would be 6t. Again, the plus 1 goes away, so we just end up with the power rule on both of them for our equation. This simplifies. The t's give you a t on top, and the 3 over 6 gives you a 2 on the bottom. So my derivative is just t over 2. And I want to set that equal to 1/2 right here. And so kind of hopefully it looks sort of obvious that if you have t squared, not t squared, you have just t over 2 equals 1/2. If you multiply both sides by 2, you end up with t equals 1. And so if I have a t equals 1, I only end up with 1 point. So there's not what point. It's just point and be done. And so I want to plug this t value back into this x and this y. So at x, I would have 3 times 1 squared plus 1. That would give me 4. And I would have 1 cubed minus 1, which would give me 0. So the only point where I have a slope of 1/2 on this entire equation would be at the point 4, 0. Okay, let's talk a little bit about area. Find the area enclosed by the x-axis to the curve. Now, it might be a good idea to have a little bit of a sketch to show you kind of what this looks like. So I'm going to do a short little sketch up here in the corner. And it's pretty much in the first quadrant, what we're going to be looking at. So that's all I'm going to draw here. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I think the y-axis doesn't have to be too big, so we'll just go 1, 2, 3, 4, 5. Okay, so what we might want to do is figure out what values this would give me so it hits the x-axis. And to hit the x-axis, your x values have to be 0. So could we find what makes my x's be 0? So I'm going to take this equation and say 0 equals t cubed plus, oh, I'm so sorry. I'm thinking of the wrong function, aren't I? Ignore all that. I need to know what makes the y 0, because that'll hit the x-axis. Uh-oh, I erased part of my 2, didn't I? This is 2 right here. There we go. I actually need this equation to be equal 0. So I need 0 equals 2t minus t squared. Factor out the t, and I'll have a 2 minus t. So either t is 0 or t is 2. So when t is 0 or t is 2, I get a function that will hit the hit the x-axis. And so if I plug those two values in back into the x, I'll get that x would be 0 cubed plus 1, which is 1. Again, I slightly erased the number 1 right there. Or if I plug in the 2, I'll get 2 cubed plus 1, which is 9. So that'll give me two different sets of points. Either 9, 0, or 1, 0. So I'm starting here, and I'm going to there. And so you may want to point somewhere along the way to kind of see how it looks like in between. So let's just pick what if t were 1. Well, if t were 1, x would be 1 cubed plus 1, which is 2. And y would be 2 times 1, which is 2, minus 1 squared, which would be 1. So I'd have to point to 1. So I end up with a curve. It's gonna, you need to see it with a little bit of concavity and such in it as well. But it basically is going to come up, and it's going to turn, and it's going to go down to that point. We want to find this amount of area inside our curve. And we can do that. Not very hard at all. So remember, when you found area back in Cal 2, area was an integral, if you remember, between 2 points, and then you integrated a function. You integrated y with respect to x. So you might have integrated like x squared dx or x cubed dx or whatever the case is. We don't have that here because we don't have a function of y in terms of x. We have x's and y's in terms of t's. So we have to do a little bit of finagling. So we're going to rewrite this. Instead of between a and b, we're going to go between, say, alpha and beta, just to pick something different besides a and b. And we're going to do g of t, f prime of t, dt. Now what this is, if you might notice, this is y. This would be your function for y. And your dx would be the derivative of x with respect to t, or the f prime of t dt. So that's what you're doing. You're going to leave the y alone, and you're going to take the derivative of the x. The alpha and the beta are your t values. So I'm going to go between 0 and 2. That would be the 0 to 2 that I found right here. G of t, which would be the y, 2t minus t squared, times the derivative of the x, 3t squared, and I integrate that with respect to t. It's going to be a power rule once we work it out. The 3t squared times the 2t will give me 6t cubed minus 3t to the 4th dt. And so we will add 1 to the power and divide by the power. We will add 1 to the power, divide by the power, and go between 0 and 2. So hopefully all of this is very familiar from Cal 2, how to integrate all this sort of stuff. So the 6 over the 4 would become 3 over 2. So I'm going to write this as 3 times 2 to the 4th over 2 minus 3 times 2 to the 5th over 5. And if you were to plug in 0 on both of them, you actually just get a bunch of zeros. So if you want to plug the zeros in, you can. If you don't, it won't matter. You'll get 0 anyway. 2 to the 4th is 16. So I'll get 3 times 16 over 2. And 2 to the 5th is 32 over 5. 2 goes into 16 8 times. 8 times 3 is 24. So this is 24. 5 doesn't go into 32. So that's not good. But it's not, I mean, it's not that bad. 32 times 3 is 96. 96 over 5. Yeah, 96. And so if I do 24 minus 96 over 5, you have to get a common denominator of 5, whatever 24 times 5 is. Let me think for a minute. 5, 2, 4, 10, 112, you get 120. And then subtract the 96. Anyway, you'll get 24 fifths. Type it in the calculator if you need to. But that's the amount of area under that curve between the curve and the x-axis. Okay, here's a theorem for you to find the length of a curve. So if you took Cal 2 this last semester, they may have talked about kind of toward the end in Chapter 8, how do you find the length of a curve C in Cartesian equations, like in x's and y's. We're actually going to do length of a curve 2 different ways. We'll do it in this section as a parametric curve, and then we'll do it again either the next section or the one after that. We'll do it in polar curves. But if a curve C is defined by parametric equations, then we can find the length of the curve by integrating each derivative squared added together between two t values. So this is just the formula that you would need to know to do the next problems. So on this one, what we're going to do is find the length of the curve using that formula, where the length of the curve is defined between two numbers as the square root of the dx dt squared plus the dy dt squared dt. And so we just need to take those two derivatives and plug them in and see what we get. So the length of the curve would be the integral from 0 to 1 of, and I need my two derivatives. My dx dt would just be a power rule. This is just 6t. My dy dt would actually be 6t squared. So I will have inside my radical a 6t that gets squared, and then I'll have a 6t squared that also gets squared. And from here on out, this is all Cal 2 material, so hopefully this part should be okay. You'll get 36t squared and 36t to the fourth. And you might notice that there is a 36t squared in common that we can factor out. And I'll end up with a 1 plus t squared left over, which is good because I can actually do the square root of 36, which would be 6. I'm going to go ahead and pull the 6 out in front of the integral. And the square root of t squared would just be t. And then I'll have a 1 plus t squared left over. Notice we're going between 0 and 1 on our integrals, so we don't need a plus or minus when we take the square root of t squared. Between 0 and 1, t would be positive anyway. But this is a u sub. You could let u be 1 plus t squared, and du would become 2t dt. And we'll change our limits as well. If t was 1, that means our u becomes 1 plus 1 squared, which is 2. Or if t is 0, that means our u becomes 1 plus 0 squared, which is 1. And so the length of the curve would become 6 times the integral between 1 and 2 of t times the square root of u. This is what becomes our u. And our dt will become du over 2t. So the 6 divided by the 2 gives me 3. And I'm left with the t's canceling. This t cancels that t. And so I'm just left with the square root of u, or u to the 1/2. And so if I add 1 to the power, this is now just a power rule. I'll add 1 to the power, divide by the power between 1 and 2. I'm going to flip the 3/2 over and multiply it. So I'm going to get 3 times 2/3 times, if I plug in 2, I'll get 2 to the 3/2 minus 1 to the 3/2. So I get a length of a curve of 2 times 2 to the 3/2 minus 1. Which is not a very pretty length, but it's okay. Could be worse. This one says, find the distance traveled by a particle with position x, y as the t varies in a given time interval, here between 0 and 3 pi, and compare that to what the actual length of the curve would come out to be. So let's try to find what would we get by doing our formula. Well, what I would get is the integral from 0 to 3 pi of the square root of, I need the derivative of x. So sine squared would become 2 times sine times cosine. It's a chain rule. You pull the power down, leave the inside the way it is, that's where the sine comes from, and the derivative of sine is cosine, that's the interior part. Plus, if I do the derivative of y, cosine squared, I would pull the power down, leave the inside the way it is, times the derivative of the inside gives me a negative sign. But it's going to get squared, so it actually won't matter one way or the other. But you might notice that's an identity. 2 times sine times cosine, that's an identity for sine 2t. So this is, like I said earlier in the last section, you'll need to know a lot of trig along the way in some of this stuff. So 2 times sine times cosine is actually sine 2t. And 2 times sine times cosine with a negative in front of it just makes it be negative sine 2t. But it does get squared. So the negative actually won't matter. So this is sine squared 2t plus sine squared 2t. So I get sine squared plus sine squared, which is 2 sine squared 2t's. So this is 2 sine squared 2t. Now the square root of 2, I can just move it out front. And the sine squared underneath the square root just becomes sine. And that's something I can actually integrate fairly easily. Now, technically, since sine is an odd function, between 0 and 3 pi, it is actually bouncing between the positive numbers and the negative numbers. So officially, this needs an absolute value on it. So what we would really want to do here is figure out what's going on where it's positive. Sine is positive between 0 and pi over 2. So we're going to kind of adjust this a little bit and say that we're actually going to go between 0 and pi over 2 and integrate sine t, because I know it's positive between 0 and pi over 2. That's the first quadrant on the unit circle. How many pi over 2 intervals are in between 0 and 3 pi? Well, you go from 0 to pi over 2, that's 1. Pi over 2 to pi would be 2. Then the 3 pi over 2 would be another. Then the 2 pi. Then the 5 pi over 2. And then the 6 pi. So there's 3 pi. So there's actually 6. There are 6 of those intervals that long. So I'll have to put a 6 out in front. So if I integrate sine of 2t, I'll get the integral of sine is negative cosine. And I have to divide by the derivative of the inside, which is the 2. And actually, this 2 on the bottom will make this 6 be a 3 out front, which is kind of nice. And the negative I'm going to pull out front. So I'm going to get negative root 2 times. I have to do cosine of 2 times pi over 2 minus cosine of 2 times 0. Oh, sorry, I left the 3 off in front. So negative 3 root 2. There we go. I'll get negative 3 root 2 times. The 2's cancel. Cosine of pi is negative 1. Cosine of 0 is 1. So I'll get negative 3 root 2 times 1 minus 1, or negative 1 minus 1 is negative 2. So I'll end up with 6 root 2. This number right here is actually the distance you traveled between 0 and 3 pi. The length of the actual curve, because what's happening is you're bouncing back and forth between these numbers, the length is actually the square root of 2, because the square root of 2 is what you would have gotten without the 6 in front. So if you were to integrate just the integral from 0 to pi over 2 of sine 2t dt, you would get root 2. This is the length. And it's kind of easier to notice in a picture. Basically what's going on is if you plug in 0, sine of 0 is 0, cosine of 0 is 1. So if I was to plug in 0 into these two equations up here, my x value would be 0, my y value would be 1. So I'm starting right here. If I was to plug in pi over 2, sine of pi over 2 is 1, squared is 1, cosine pi over 2 is 0. So at pi over 2, I'm at this point. And I'm basically going from here to here. If I went from pi over 2 to pi, all I'm doing is going back to here. And then the next one would go back down and up and down and up. So you're just you're going back and forth. You're transversing that same line 6 times between 0 and 2 pi. Or sorry, between 0 and 3 pi. And so you're going back and forth 3 times. But the length of the curve is just how far is it from this point to this point only. That's why this root 2 is the length. And I hope that makes some sense.